In this video, we're going to cover sections 7.4 and 7.5, which looks at the stereochemistry of the SN2 reaction and the E2 reaction, as well as the regiochemistry of the E2 reaction. Now, the observed stereochemistry of the SN2 reaction is consistent with a concerted mechanism. And so when the alpha position is a chirality center, a change in configuration is generally observed. So in an SN2 reaction, we will refer to this change in configuration of the chirality center as an inversion of configuration. And we refer to this reaction as also being stereospecific because the configuration of the product is very much dependent upon the configuration of your starting material or your substrate. So as you can see in this example, if we have this particular alkyl halide, okay, so we have a secondary alkyl halide, and the nucleophile is this hydrosulfide ion, so we know this is a very good nucleophile. Secondary alkyl halide, some steric hindrance associated with this methyl group and this ethyl group, but SN2 reaction can occur between these two species. Notice that we have a chiral center, so there's 4 different groups attached to this carbon, and this carbon is the alpha carbon in the reaction. And so what we observe is that the chirality, or I should say the configuration of that chirality center, changes as we go from our reactant to our product state. So this nucleophile will most likely attack 180 degrees away from the leaving group, and we'll have loss of the leaving group. In doing so, this nucleophile, in a way, in a sense, it's going to push these groups away from its incoming trajectory. In a sense, these groups get aligned towards where the leaving group once was. And so you can see that if we compare this species to this species, these 3 groups, this is the mirror image of those 3 groups. And so that gives rise to this change in configuration. So when we look at this in more detail, as shown below, we have nucleophilic attack onto the alpha carbon and loss of the leaving group. This occurs simultaneously. This is the concerted mechanism for the SN2 reaction. Now, what do we observe at the transition state? Well, we've mentioned previously, in the previous video, that at the transition state for an SN2 reaction, we are forming a new bond between the sulfur atom and the alpha carbon. And at the same time, the original carbon-bromine bond, the leaving group, it is starting to break. And so the transition state can be drawn as such. So if we have our chirality center, we have our ethyl group, and then coming out towards us is our methyl group. And what's not being shown, what is being shown for clarity is the hydrogen atom. And this alpha carbon, there's an incoming nucleophile, the hydrosulfide ion. And there's the outgoing leaving group, the bromide. Now there's a partial minus charge associated with both the incoming group, which is carrying some additional electron density as the anion, and as well there's going to be some partial negative charge associated with the leaving group because the bromine atom is very electronegative. So when we look at this transition state and more closely, the way that these groups are arranged, they're arranged somewhat in a plane. So the ethyl group is drawn straight down, and what's coming also directly towards you is the methyl group, and what's directly behind that group is the hydrogen. So we think of this as almost like an sp2 hybridized center in a sense. And what's coming in is your new sulfur carbon bond, or the nucleophile attacking the alpha carbon, and what's being left behind or being lost in this process is this carbon-bromine bond is breaking, and you end up with the bromide as your leaving group. So as the hydrosulfide ion comes in from this direction, you can see that around this central alpha carbon, everything somewhat goes flat in a plane, and then it's pushed over, if you will. And sometimes in the textbooks, they'll refer to this as inverting the umbrella, whereas you have this part of the molecule as, let's say, the dome of an umbrella, and what's coming to the inside of that, or under that umbrella, is the nucleophile, and then it flips inverts the umbrella. It flips it inside out. And so as a result of that movement, if you will, of these groups around the chirality center, the movement of those from this direction to this direction leads to this inversion of configuration. So this is something we observe for SN2 reactions. So with the E2 reaction, we can also have different regiochemical and stereochemical outcomes. So when we talk about regiochemistry, it's referring to the placement of a particular group. In this case, that group we're referring to is the double bond in the structure. You can see that starting from this particular alkyl halide, it's possible to form two different alkenes, which have the same constitution, same number and types of atoms, but the connectivity is different. You can see we have a double bond, which leads to a tri-substituted alkene in this example, or if the double bond is located here, we end up with a di-substituted alkene. So we're going to look at the reasons behind this possible product mixture that can be obtained from an E2 reaction. So we have to recall that in our E2 reaction, this is the base removing a proton from the substrate. So you have a hydrogen atom attached to a beta carbon, either here or here, which is, in a sense, donated to the base. So the base picks up this hydrogen atom as a proton, forms the pi bond, and the leaving group is lost. And this is a concerted mechanism, single transition state, showing the interaction of the base with the substrate and the eventual loss of the leaving group. So depending on which hydrogen is involved in that E2 reaction, if it's here, we're going to end up with this particular alkene. If this is a hydrogen that's lost as a proton is to this beta carbon, then it's between this alpha and beta carbon in which the pi bond will form. So let's look at why or how we can control this particular product formation, this regiochemistry. Furthermore, a reaction is said to be regioselective when it can produce two or more constitutional isomers. And in general, the more substituted alkene is observed to be the major product. We call this product the Zaitsev product, whereas the less substituted alkene is often called the Hofmann product. In table 7.4, we look at the product distribution of an E2 reaction as a function of the base that's used. And for our purposes, we can ignore the last example, but we'll focus in on the other two. So the ethoxide, which can also be drawn in this manner, and the tertiary butoxide drawn below, which can also be abbreviated TBUO-. If we compare how, when these bases are used, how the product distribution is obtained, we observe that for the ethoxide, we generate about 70% of the more highly substituted alkene, whereas only 30% is of the di-substituted. Now this ratio virtually flips when we use the tertiary butoxide. And the reason for that has to do with steric hindrance. And so the nature of the size of these particular bases gives rise to this difference in product distribution. So when tertiary butoxide is used, we refer to this as a sterically hindered base or a bulky base. When this is used, access to the more highly substituted beta carbon is limited. And so as a result, more of the alkene will form to which the beta carbon is less hindered. So here we have a CH3 group, here a CH2 group attached to a methyl group. The bulky base has a more difficult time accessing this particular beta hydrogen due to sterics. So the majority of the product is a result of this hydrogen being lost as a proton when tertiary butoxide is used. And so we form more of the Hofmann or the disubstituted alkene when the bulkier base, the tertiary butoxide, is used because it just has easier access to this particular beta carbon hydrogens, so the hydrogens attached to that beta carbon. Now the ethoxide doesn't have the same steric hindrance associated with it, and so the preference will be to produce more of the more highly substituted alkene, which is the more stable alkene. So when ethoxide or methoxide, when those two strong bases are used, we're going to see that the majority of the alkene that is formed will be the tri-substituted, and that's because that alkene is more stable. So we refer to this type of selectivity as regioselectivity. Now, before we look at the stereochemical outcomes of the E2 reaction, we want to define and sometimes redefine a couple terms. So a reaction is said to be stereoselective when the substrate can produce two stereoisomers as products, but in unequal amounts, meaning it has a preference for one stereoisomer over another. So you'll have a major product and a minor product. However, a reaction is said to be stereospecific when the substrate is stereoisomeric and results in one stereoisomer as the product. And we saw this in our last example with the SN2 reaction, that it is a stereospecific reaction, and that depending on the stereochemistry of the reactant, the substrate, we will observe a particular stereochemistry of the product. We saw that there was an inversion of configuration in the SN2 reaction. So if we started with an R configuration, we most likely will end up with an S configuration, whereas if we started with S, we'd end up with R. That is different than a stereoselective reaction, which would produce two different stereoisomers. We don't observe that type of stereoisomerism or stereoselectivity for the SN2 reaction. Now, in this example shown below, we have two beta positions again, 1 and 2. But in this example, they are identical. So there's not going to be the same regiochemical outcome that we saw in our previous E2 example. But what we will observe when this base is used, sodium ethoxide, so again, if you see a sodium, it is simply the counter ion. This is what we are generating, and this is our active species. So in this particular reaction, the ethoxide will produce this particular alkene, but it can also form this particular alkene. And the difference between these two products is not in the nature of their substitution. They're both disubstituted alkenes. The difference between them is that they are stereoisomers of one another, diastereomers. And so we see that we can obtain both the trans alkene as well as the cis alkene. Now, the major product of this reaction will be the trans alkene, and we mentioned earlier that this has to do with a steric interaction that is associated with the cis, that there is potential steric hindrance or steric interactions between the methyl group here and the ethyl group on the same side of the double bond. And so shown in this potential energy diagram, you can see that the energy, the relative energy of the trans isomer is lower than that of the cis. And so that lowering of the energy associated with that particular isomer gives rise to it being produced in a greater amount. So the trans isomer will be formed as the major product, and the cis isomer will be formed as the minor product. As a result, this reaction is considered stereoselective because we observe the production of two different stereoisomers, one of which is formed in greater amounts. Now, let's look at some examples of stereospecificity that, depending on the stereoisomer that you start with, what type of products will you observe? So we're going to look at a few different examples. This example, you can see our starting alkyl halide. We have only one beta position that has a hydrogen. It's this position here. So this beta carbon has three methyl groups attached to it. It's a tertiary butyl group. So there are no hydrogens available for an E2 reaction. And so the only other beta position available is this, and we have a single hydrogen attached to it. So this will be the hydrogen that's removed as a proton by the base. And the double bond will form between this alpha and beta carbon, and this will be our leaving group. And what you may not be familiar with is this symbolism. This pH refers to a phenyl group. I'll just draw that up over here. But the phenyl is equal to the following. It's a substituent. It's the benzene ring as a substituent. So this is your phenyl group. I'll just draw a squiggly line to represent that that's bound to something else. Nonetheless, when we have our E2 reaction, the base, so I'll use the ethoxide again as an example, it's going to remove this hydrogen as a proton. We're going to have the formation of a pi bond and loss of the leaving group. So this all occurs in the E2. Now what's important in this reaction is that the hydrogen that's deprotonated by the base and the leaving group, the bromo group here, that these are 180 degrees away from one another, and they're in the same plane. And so the way the structure is drawn is that this carbon-hydrogen bond, carbon-carbon bond, carbon-bromine bond, they're all in the plane. Okay, they're all what we call coplanar. And as a result of that coplanarity, we will end up with one particular stereoisomer. You'll see that once this is deprotonated and this is lost with the new formation of the new pi bond, that the phenyl group and the hydrogen will be on the same side of the double bond. Those are the two groups coming towards you. And the methyl group and this tertiary butyl group, they're behind the page, they'll be on the same side of the double bond. And so this is the only product that we observe from this reaction, where again, the phenyl and the hydrogen, which were on the solid wedges, they are on one side of the double bond, and the methyl and the tertiary butyl group are on the other side of the double bond. So these groups are, in a sense, cis to one another. We don't form this particular stereoisomer. We don't see the same cis-trans, if you will, isomerism in this particular example. So this is not a stereoselective reaction. This is a stereospecific reaction. So to understand the stereospecificity of this reaction, we need to look at the transition state for this reaction. So in the transition state, as I've just said, the carbon-hydrogen bond and the carbon-bromine bonds that are breaking must be rotated into the same plane as the pi bond that will eventually form. That is, these four atoms, hydrogen, carbon, carbon, bromine, they must be coplanar. And so, as much as there are two possible conformations in which we can draw for this particular structure, the one that will actually lead to the formation of a product is when this carbon-hydrogen bond and this carbon-bromine bond are 188 degrees away from one another. So yes, we have two possible conformers. Remember back to our Newman projections. There's two possible conformations that we can draw for this particular substrate, which places these four groups coplanar with respect to each other. Now here are the two Newman projections that would describe those two scenarios. If we have the carbon-hydrogen and carbon-bromine bond 180 degrees away from one another, we refer to this as the anti-coplanar. You'll recall that this is one of our staggered conformations. So we have the anti-coplanar situation where the bromine and the hydrogen are anti to one another. As well, the other conformation leads to an eclipse conformer, and we call this the syn coplanar. And so recall that the energy of the anti-conformation is much lower than the energy of the eclipse conformation. And so this will be the more stable conformation for this particular substrate in our E2 reaction. So as a result, the elimination reaction occurs exclusively via the anti-coplanar conformation, as shown. As a result, you can see that the anti-coplanar will lead to this particular product, which places the phenyl and the hydrogen on the same side of that newly formed double bond, and the methyl and the T-butyl group on the same side of that double bond. And so that will lead to this one stereoisomer. And so as a result, we refer to this as a stereospecific reaction. Now, in reality, coplanarity is not always entirely possible or absolute. There will be small deviations from coplanarity that will still result in a successful E2 reaction. And so the idea is that the dihedral angle should be as close to 180 degrees as possible, but doesn't have to be exactly 180. So the term periplanar is also used to describe this situation where they're nearly coplanar to one another. And so the term that we'll often see used is anti-periplanar as opposed to anti-coplanar. So although the E isomer is usually the more stable because it's less sterically hindered, the requirement for anti-periplanar transition state can often lead to the less stable Z isomer as well. So in other words, the stereoisomeric product of an E2 process really depends on the configuration of the starting alkyl halide, and as a result, we refer to these types of reactions as being stereospecific. So let's look at a couple examples of the E2 reaction, which we assume proceeds through an anti-periplanar transition state. So let's predict the products based on that information. So the base isn't specified, but let's use our ethoxide. And our curved arrow, we have the hydrogen leaving as a proton, formation of our pi bond, and loss of the leaving group. And so what we want to focus on is when these four atoms are coplanar, particularly anti-periplanar. So when these four atoms are anti-periplanar, the E2 reaction will occur from that transition state. And in this situation, both the R1 groups are going to be on the same side of the double bond, and the R2 groups, which are behind the page, will be on the same side of the double bond as well. So our alkene will look something like this. And I can keep the colors the same for clarity. That those two groups will be cis to each other. And the R2 substituents, just other alkyl groups, similar alkyl groups, they'll be also cis to one another. Now in the example below, a slightly different scenario where we see that the placement of R1 and R1 on different carbons, the alpha and beta carbons, they are on different sides of the plane. So in this example, we're going to have, we make R1 on this side of the double bond. The other substituent shown here in red will be on the opposite side. And R2s will also be trans to one another. So these are the two stereospecific products of this particular E2 reaction. So the requirement for an anti-periplanar arrangement, this determines the stereoisomerism of the product. In other words, the stereoisomeric product of an E2 reaction depends on the configuration of the starting alkyl halide. Now the stereospecificity of an E2 reaction, this is only relevant when both the alpha and beta carbons are stereocenters and the beta position only has a single proton. If, however, the beta position has two protons, then either of these two protons can be arranged such that it is anti-periplanar to the leaving group. In this situation, both stereoisomeric products will be obtained. And so this is a case where it's not stereospecific, the reaction is considered stereoselective because more than one stereoisomer is formed, and the more stable isomer will be the major product. So when you can obtain products major and minor, we refer to these as stereoselective reactions, not stereospecific reactions. So we can't, based on the information provided in this example, decide which is the major product because we don't know the nature of these R groups. But we would try to minimize the steric interactions between them. So we would like to place small groups, if you will, on the same side of the double bond as opposed to placing two larger, bulkier substituents on the same side of that double bond. But you can see in the example here, starting from this particular anti-periplanar arrangement, that we would generate this particular stereoisomer. But if we were to rotate around this alpha beta carbon-carbon bond, if we were to rotate this hydrogen into the plane associated with this carbon-carbon bromine plane, that would then generate this particular stereoisomer. So again, the stereoselectivity will depend on the nature of the R groups, but this is not considered a stereospecific reaction because that would imply, depending on what this configuration or stereoisomeric properties of this compound, will give a single stereoisomer as a product, and that's not the case for this example. So let's look at a couple of examples where we may have either stereospecific outcomes or stereoselective outcomes from the elimination reaction of an alkyl halide. So in this question, let's identify the major and minor products for an E2 reaction where this is the substrate, this alkyl halide is undergoing a reaction with a strong base. Now, the first thing to do in these types of questions is to identify the beta position and to look at those beta positions for potential sources of protons. So we have two beta positions in this particular alkyl halide. We have a beta position here and a beta position here. So two beta carbons. Now we're looking for beta hydrogens, hydrogens attached to those beta carbons. There are no hydrogens attached to this beta carbon, so there'll be no protons available for donation in this E2 reaction. However, there are two protons that are potentially available at this position. So there's two beta hydrogens. They can be protons involved in the E2 reaction. Now, because there are two protons at the beta position, as shown, we won't have a stereospecific reaction. This will be an example of a stereoselective reaction. So what we would expect from the stereoselective reaction of this alkyl halide would be both a cis and a trans isomer. So let's draw the cis and trans isomers of this particular E2 product. So we have our phenyl ring, not involved in the reaction, and we will form an alkene at this location. And so what I've drawn is the trans. You could also refer to this as the E. And also we will have the cis isomer. As shown, and this could also be referred to as the Z configuration. So these are the two stereoisomers that we expect from this E2 reaction, and the major product will be the trans stereoisomer, and the minor product will be the cis. And again, that's due to the steric hindrance or steric interactions associated with having this phenyl group and this ethyl group on the same side of the double bond. So the major product is the trans isomer. Now let's look at an example where we obtain a stereospecific product. So let's identify the major and minor products for the E2 reaction when this substrate is treated with a strong base. Now, when we look at this particular alkyl halide, we notice that there are two beta positions. There's a beta position here and a beta position here. But only one of these positions bears a potential proton or a hydrogen. There are no hydrogens attached to this carbon. It's fully substituted with methyl groups, i.e. the T-butyl group, whereas this beta hydrogen does have a single hydrogen that's available to be donated to the base as a proton. So this beta position only has one proton, so the reaction will be stereospecific. So what we expect is only one stereoisomeric product from this E2 reaction. So to determine which product we should expect, one way to treat these questions is to draw the Newman projection for this particular structure when we look down this particular angle or perspective. Okay, so let's do that. Let's draw our Newman projection for this particular compound. So when we look from this particular perspective, the first thing you should notice is that this phenyl group is in the same plane as our carbon-carbon single bond that we're looking down. And this T-butyl group is also in the same plane as this carbon-carbon single bond. So this group will come directly vertical on our Newman projection, and this group will also be in that vertical axis, but pointing in the downwards direction. So this group is below this line, and this group is above the line. And the line is that carbon-carbon sigma bond, of which we are drawing a Newman projection about. So let's draw that in. And so the carbon in front is attached to this particular ring system. We can abbreviate this with the symbol pH to represent a phenyl group. So we'll do that. So we have a phenyl substituent attached to that carbon in front. So now let's draw the T-butyl group that's drawn below the plane, and we'll use the symbol T-BU to represent that T-butyl group. Now with respect to the remaining atoms attached to those two carbons, again, this is a staggered conformation. So we're going to have two groups attached to the carbon in front that haven't been drawn, and the two remaining groups in back. Now when we're looking down this carbon-carbon bond, we have a methyl group and a bromo group. So a bromo substituent and a methyl substituent, and they're both behind the plane being the plane representing these bonds on our page. So if we're looking from this direction and they're behind the page, they're going to be on the left-hand side of our axes. So the bromine is going to be above that plane and on the left, and the methyl group will be down and to the left. And so what's remaining at each of these positions is a single hydrogen, and they'll both be coming towards us. We don't show them in our bond line structures, but they are coming towards us. And so therefore, from this perspective, they will be on our right-hand side. So the next thing to do is to identify the proton and leaving group that will be removed during this elimination reaction. And as you can see in this particular conformation, the leaving group is antiperplanar to a hydrogen atom. And so this will be the hydrogen atom in this conformation that will be removed with the leaving group in our E2 elimination. So we have the base coming in, removing this hydrogen as a proton, these bonding electrons becoming the new double bond or pi bond between the two carbons in our Newman, and this bromo substituent will leave as the bromide. And so once we identify which our leaving group and the antiperplanar hydrogen that will leave as a proton, then it's easier to see during the formation of the double bond, which will occur in this plane, which groups will be on the same side of the double bond with respect to each other. So which groups will be cis to one another. So in this example, the phenyl and the hydrogen, they will be cis. They will be on one side of the double bond, and the methyl and the T-butyl group will be on the opposite side of that double bond. So we can show that. We add our base and we carry out the E2 reaction. We can redraw this particular conformation in the following way. And again, the double bond is this plane, and so we can redraw our bond line structure. So this conformation is equivalent to the following. And so we have the phenyl and our hydrogen that we're not showing cis to one another, and the methyl group and the T-butyl group are also cis to one another. So if we want to determine which configuration is being shown in this particular alkenol product, we can go through our high-low priority rules on each particular carbon. So if we look to the carbon on left, this carbon here, we have a carbon and a carbon. Remember, this is what the phenyl group is referring to. So we have carbon, carbon. So then we have to go to the next set of atoms. Attached to this carbon are 3 hydrogens. So I can remind us here. And attached to this particular carbon would be carbon, carbon, carbon. And so this will be our high priority group. The phenyl ring will be higher in priority than the methyl group. So let's do the same on the opposite side. So here we have a hydrogen T-butyl group. The T-butyl group is going to be higher than the hydrogen. It will always be the lowest priority group. So the two high priority groups are across the double bond. They're on either side of the double bond. So this gives us our E stereoisomer. So again, we only have a single stereoisomeric product. We generate the E alkene E isomer as a result of this E2 elimination. So I'm going to clear this particular page and show you another way in which you can determine which stereoisomeric product you'll obtain from an E2 reaction of this particular alkyl halide. This second method is explained in chapter 7 of our text, specifically in Skill Builder 7.4. So I'll go through the process that they've used to look at this particular example. So in this second approach, what we're going to do is we're going to rotate the carbon-carbon bond axes such that we will place the leaving group in the plane and the beta hydrogen at this carbon also in the plane. In some ways it's a little bit more work, but for some it may be an easier way to approach this type of question. So the first thing we're going to do is I'm going to redraw this structure that shows both hydrogens at the alpha and beta position for clarity. So let's do that. So this structure is equal to the following. And I'm going to draw a hydrogen at the alpha position, and using my three-dimensional bond show the bromine atom. And I'm going to again use the symbol pH for the phenyl ring just to save some space. And so we have the phenyl ring in the plane. We have a hydrogen that's not being shown coming out towards us. And then we have that methyl group. All right. So the first thing we're going to do is we're going to rotate this structure. So if we're looking end on now, so I've changed our perspective. We're looking in this way, down a single bond. So change the perspective slightly. And so we're going to rotate such that during this rotation, the phenyl group that's now in the plane is going to rotate towards us. The hydrogen that's towards us now is going to move towards the plane. And the methyl group that's currently behind the plane but facing downwards, as you rotate that particular tetrahedral, it will come up, but still be behind the plane. So we'll do that first. So upon rotating, we're just rotating these groups around this carbon-carbon single bond. So let's redraw that structure. We're going to keep everything on the right-hand side all the same. So we have our bromine, we have our hydrogen, and our T-butyl group. And then what is new after our rotation is that the hydrogen will be in the plane. Our methyl group will be behind the plane, but above on the top side of that carbon-carbon single bond. And the phenyl ring is now facing towards us. All right, so now the next thing to do is to rotate this particular carbon center along this carbon-carbon single bond so that this bromine atom is in the plane. So how we'll do that is we're going to rotate in, I guess, the opposite direction. We're going to, this bromine isn't back, we're going to rotate it in a, if you're looking from this direction, we're going to rotate this structure, this N carbon, in a counterclockwise manner. So in doing so, that bromine atom is going to be up and in the plane. The hydrogen that's towards us is going to rotate down but still be in front of us. And the T-butyl group that's in the plane, as we rotate in that counterclockwise manner, it will go behind the page and facing downwards. All right, so let's look at our structure now. So we have our phenyl ring, our methyl group, our hydrogen in the plane. Now we'll have our bromine atom in the plane, a hydrogen coming out towards us, and in back we'll have this T-butyl group. All right. So now, after doing those two rotations of each carbon such that the leaving group, this bromo substituent, is anti-perplanar to a beta hydrogen. And so it'll be this beta hydrogen, of course, that will be lost. And so in drawing our mechanism, let's use our base lone pair, and we're going to carry out our E2. All right, so the net result of that reaction is the following. We're going to end up with our alkene with the T-butyl group in behind. This hydrogen will be in front. We will have our methyl group in behind and a phenyl group coming out towards us. And so we can redraw this in our bond line structure where now we're looking at it kind of at the edge with the phenyl and hydrogen coming out towards us, but we can redraw that slightly to make it a little bit more clear. So we have our alkene, we're going to have our T-butyl group, methyl group, and then I'll just use pH again for clear. So that is our stereoisomeric product. It's our stereospecific product. It's the only product that we'll get from this particular reaction. And again, this is the E isomer. The phenyl group is, which is the highest priority group, is on the opposite side of the other high priority group, which is the T-butyl group in this example. So you can use either approach to determine what the stereospecific product would be for this particular E2 reaction. You can draw a Newman projection, or you can use this strategy where you rotate the two carbons of the sigma bond such that the leaving group and the hydrogen on the beta position are antiperplanar to one another. If you want some additional practice with this style of question, practice the skill 7.21 has some additional problems that you can try. And if you have any questions about the stereochemical outcome of SN2 and E2 reactions, or the regiochemistry with respect to E2, by all means, you can send me a message or an email, and we can, if necessary, set up a Zoom appointment. Thank you.